Hi guys, Mrs. Rossi here. Today we're going to be talking about phase changes. You're going to follow along on your class note sheet as I talk. If you need to pause, go back, anything like that during the video, make sure you do that so that all blanks are filled in and all questions are answered. So today we're talking about phase changes. So we know this is going from one state of matter to another. If you look at this front picture, we have a very orderly, pretty tightly packed together example of matter. So you could assume this is a solid. These ones are a little bit more spread apart. Looks like there's a little bit more motion of particles. We would assume that this is a liquid. And then over here, really spread far apart and less particles. They're trying to get away from each other. We would assume that's a gas. Another name for these phase changes that take place is changes of state. So changes of state, phase changes, they mean the same thing. And in either case, it's all about adding or removing energy. So to go from one to the other, if you're going to go from a solid to a liquid to a gas, you're going to be adding energy to get there. To go from a gas to a liquid to a solid, taking away energy. A change of state is a change of a substance from one physical form to another. All changes of state are physical changes. So when you go from a solid to a liquid, if you're talking about water, the chemical formula doesn't change. There's no change in the bonds that are made or the bonds that are there. So you're not making new bonds, you're not breaking bonds, still same chemical formula, so it's a physical change. When you look at this diagram, it compares a couple different factors about when phases change. So we have temperature first. To go from a solid to a liquid to gas, the particles increase in temperature. And if you increase in temperature, we know from the kinetic molecular theory that those molecular motions are also increasing. So those particles have more energy, they're moving around faster. So solid would be the least molecular motion, liquid, some molecular motion, and gas, we know those particles are moving really fast. And then the last factor that they're comparing them between are molecular interaction. So how much interaction those particles have with each other. So in a gas, we know that they bounce right off of each other. The kinetic molecular theory tells us that too. In a liquid, we know that they just are sliding past each other, so there is some attraction there. And then in a solid, there's lots of attraction. They're kind of locked into place, vibrating in a solid. So particles have different amount of energy depending on the state that they're in. And that really shouldn't be so surprising, thinking back to that kinetic molecular theory and thinking back to what we know about how particles in each state of matter behave. To go from one state of matter to another, you either have to add or remove energy. So to go from a solid to a liquid, you need to add energy to break that particle attraction. To go from a liquid to a solid, you need to remove energy so that they kind of lock into place. There's a more scientific way to describe what happens when changes of matter occur. Exothermic and endothermic changes can describe what happens during different phases of matter changing into each other. These words should hopefully sound familiar to you. Last year, you probably talked about exothermic and endothermic reactions. So exothermic, think exo, exiting, therm, heat exiting. So it's describing the release of energy in the form of heat. So heat is being removed. Exothermic processes are condensation and freezing, because to go from a gas to water, you need to remove some of the heat from that gas phase and get those particles to slow down and kind of clump together. You're removing energy to do that, so heat is exiting. Exothermic, removing energy. Then to go from water to ice, so from liquid to solid, you're freezing it, you're slowing those particles down even more, locking them into place. So exothermic, because heat is exiting to make that happen. Endothermic is the opposite. Heat, therm, going in, endo. So energy is being absorbed and going into that system. So you're adding energy. So if you have a solid like ice, to melt it, you need to add energy. You need to add heat to do that. So it's an endothermic process. Same thing to get water to go to water vapor. Evaporation can happen, or even boiling can happen. As a overall term, we can also call that vaporization. I would take any of those as correct answers to go from water to water vapor. So from the liquid phase to the gas phase. Any of those are endothermic processes. On the back of your first sheet of your class notes, I've already made this chart for you. As I talk about each phase change, you're going to write down the definition and how the particles behave. You're also going to tell me whether it's endothermic or exothermic and give me an example. The example can be just written out, or if you want to draw a picture, that's great too. All right, our first phase change is melting. Melting is the change of state from a solid to a liquid. To get something to melt, you have to add energy. So energy is required to go from that solid phase to the liquid phase. That energy is used to overcome the attractions that hold those particles together. So since you're putting energy in to make melting happen, it's an endothermic process. So endothermic process, you can say ice cream melting, a snowman melting, anything like that would be a great example. Up next, our next phase change is freezing. Freezing is the temperature at which a liquid changes into a solid. Each type of liquid has a different freezing point. So we are most familiar with the freezing point of pure water, which would be 0 degrees Celsius or 32 degrees Fahrenheit. What's also interesting, which you might not think about right away, is that this is also the melting point. So freezing points and melting points occur at the same temperature. So if you are at 0 degrees Celsius, you can add heat or add energy and you'll melt it, or you can continue to remove heat and you'll freeze it. So 0 degrees Celsius or 32 degrees Fahrenheit is that special freezing point, melting point for pure water. Different liquids, depending on what liquid it is, has different freezing and melting points. They always occur at that same temperature for that one substance though. But back to freezing. Freezing is an exothermic change because energy is removed from the system. So you're taking away energy, you're slowing those particles down to make freezing occur. So particles are slowing down, they're clumping together, they're locking into place, vibrating to make that solid. Up next, we have evaporation. So for evaporation, we're talking about the change of a substance from a liquid to a gas. Now, there's a couple different terms for going from a liquid to a gas. Evaporation is the one that occurs at the surface of the liquid. So it's the particles at the surface of a liquid being changed from a liquid to a gas. This always happens below boiling point. Boiling, as you may know, has the same phase change take place. It just happens in a different way. Boiling happens throughout a liquid and not just at the surface. To get this to happen, whether it's evaporation or boiling, energy has to be added to the liquid. So since you're adding energy in, energy's going in, it's endothermic. Those particles are speeding up. An example of evaporation would be sweating. So your body's cooled through evaporation. You sweat, it doesn't stay on there. Those particles evaporate off. If you've ever been to the beach in the summer, you go in the salt water, you lay out back in the sun, and eventually you just have salty skin. You're no longer wet. Evaporation. All right, up next we have condensation. So this is the reverse of evaporation. It's the change of state from a gas to a liquid. So these, just like the freezing point and melting point, happen at the same temperature for a substance as well. So energy has to be removed for condensation to happen. So you're going from the gas state to the liquid state. You need to slow those particles down, make them clump together. Because you're slowing them down and making them clump together, heat and energy are exiting, so it's an exothermic process. You probably have seen condensation on the side of glasses on a hot day. It's not the liquid from inside coming out, it's the coldness and the warmness of the room, and then it forms and slows down those particles near the glass to make those little droplets. Up next is one that you may have only seen a few times. Sublimation is a change of state from a solid directly into a gas. So the classic example for sublimation is dry ice. If you have never played with dry ice before, don't worry, we'll be doing it in class. So you're going to be going from a solid state, so really tightly packed together, to a gas state without ever becoming a liquid. So if you have dry ice and you put it out on the lab counter is not going to get wet because it goes from a solid to a gas. So from particles being super tightly packed together to super, super spread out. Because of this, going directly from the solid to a gas, it's endothermic. A lot of energy is added really, really quick. And then the last one, the reverse of sublimation, is deposition. Deposition is something we've probably all seen. You probably just didn't know what it actually was. So deposition is the change of state from a gas directly into a solid. An example of deposition is frost. So if you've ever seen frost form on little blades of grass when it's starting to get cold out, or even on your windshield on really cold nights, it's taking the gases that make up the air and super freezing them so quick that they never go through that liquid stage and they just become solid. Because this change happens so quick, deposition quickly removes all that energy, all that heat from the gas. It's an exothermic change. Energy is lost by the substance and lost quickly. Just one more point back to the boiling versus evaporation. Boiling, like we said before, is the change of liquid into a gas, just like evaporation is the change of liquid to a gas, but how it happens differently. So evaporation, like we mentioned before, only occurs at the surface of the liquid. So once these surface particles evaporate, then you'll have new ones at the surface and they evaporate, and so on and so on. Just like what you see happening to puddles after it rains. Eventually they're not there anymore because they have all evaporated back into the atmosphere. Boiling is different. Boiling happens throughout an entire liquid. So those bubbles in there happen throughout. You're applying a heating source. So it could be the Bunsen burner if we're in lab. It could be your stovetop if you were at home. And those particles are getting quickly changed into that gas phase. So you're using energy to make this phase change occur. All right, on your paper, you're looking down at numbers 12 and 13, because now we're going to be talking about the graphical representations and what is actually going on as we go from a solid, liquid, gas to those particles. So when most substances lose or gain energy, one of two things can happen. The temperature can change or its state can change. The temperature of a substance is related to the speed of the substance's particles. And this is going back to that kinetic molecular theory. We already knew that. The temperature of the substance does not change, so it remains the same until the change of state is complete. So for example, if you were boiling water, we know that happens at 100 degrees Celsius or 212 degrees Fahrenheit. Until all of that water has been boiled off or has changed into the gas phase, that liquid is going to stay at that temperature. So during a phase change, temperature remains constant because all of the energy is being used to break apart those particles and break apart those attractions that it has. So during a phase change, temperature remains constant because all of the energy is being used to break apart the particle attraction. Take a look at this diagram. So notice that heat energy is along our x-axis, temperature is along our y. So if you have something in the solid state, like ice, let's just compare this to water or H2O. We have ice in the solid state. The temperature is going up as more and more heat energy is being applied. Temperature going up, temperature going up, temperature going up, until we get to the melting point. Now remember, melting point and freezing point occur at the same temperature. So if we're talking about pure H2O, this is happening at 0 degrees Celsius, and this temperature remains the same. So 0 degrees Celsius until all of it has melted, if we're following the graph this way. So once all of it is melted, then the temperature starts to rise because we're now all in the liquid phase and those particles can continue to be heated up. So all of the energy that was being put in, because heat energy continued to be put in at this point, was being used to break apart the particle attraction. And we know there's a lot in solids. So it took all that energy to break apart those particles. Then the liquid can be heated, can be heated, can be heated, can be heated until it gets to, and if we're heating, boiling point or evaporation point, vaporization point might be a better way to describe it. So once we get to this point, all of the heat energy, again, is being used to break apart the particle attraction so that those particles are spreading out, spreading out, spreading out, spreading out, and the temperature remains constant. If we were boiling this water, this would happen at 100 degrees Celsius or 212 degrees Fahrenheit. So this phase change takes place and the temperature doesn't change until all of the substance is now in the gas phase, and then it can continue to be heated and continue to increase in temperature. This is another phase change diagram. This is called a triple point diagram. It's just another way to represent phase changes, but this time, instead of relating heat energy and temperature, we're relating pressure and temperature. The line that separates any two of the regions, so notice we still have solid, liquid, gas, shows where those phases can exist in equilibrium at that specific temperature and that specific pressure. Right here is a special point called the triple point. A triple point is where a gas, a liquid, and a solid phase of a substance can all exist at once. It's a very special temperature and pressure of that substance. So triple point, the pressure and temperature at which all three phases can coexist. And then another special point on this graph is up here. The critical point is the highest pressure and temperature where you can tell the difference between the gas phase and the liquid phase. So this is the highest temperature and pressure you can get to, where you can still tell the difference between those. Once you get higher on either end, past this point, you can't really tell. All right, after you have that all labeled, I want you to look at number 17. There's a scenario about a scientist and her assistant. Read that very carefully, and then on your note sheet, tell me who is correct and why. Thanks for watching.